Hi, I'm going to talk about modeling and simulation of adsorption of gases from natural gas in FPYEu Metal-Organic Framework. VY adsorption is one of the most promising and widely used for natural gas separation and purification. Adsorption tends to be low-energy technology, especially when compared with liquid absorption processes. It is non-toxic when compared with ionic liquids, not prone to problems with corrosion when compared with chemical absorption, and is a robust and proven technology for gas separations compared with membrane permeation, which can be seriously damaged by some free liquids. Is molecular simulation important in adsorption? Molecular simulation helps to understand experimental adsorption results by providing a detailed picture on the molecular level that is not possible from experimental methods. Molecular simulation is quicker than experiment and reducing the time and capital investment on experimental work. One of the most popular simulation methods is Monte Carlo simulation, which is widely used to calculate adsorption isotherms of a given MOF by quick study of the impact of molecular scale properties such as surface area, pore size or pore shape on the adsorption performance for specific applications. Why did we select FPYEu MOF? FPYEu MOF is an example of a photoluminescent MOF with luminescent properties, three-dimensional structure, and the capability to withstand high temperatures up to 350–400 degrees centigrade in air, displaying both porosity and selectivity, with the potential to be used as a hydrogen sulfide sensor at low pressure. We selected FPYEu MOF as a model MOF for studying methane, ethane, hydrogen sulfide and water from natural gas adsorptions using molecular model simulation to assess the applicability of the available force fields that describe the gas-solid interactions in this system and to evaluate whether the result is sensitive to the distribution of different metals in the system. What are metal-organic frameworks, MOFs? MOFs are a special type of hybrid porous materials constructed by the assembly of organic linking units with metal clusters. The numbers of linkers that can be connected to a metallic center depend on the coordination of the metal and its oxidation state, which result in three-dimensional structures with different topology. What is molecular modeling? Molecular modeling is the collection of all theoretical methods and computational techniques used to model and study the structure and behavior of molecules. What is Monte Carlo simulation? Monte Carlo, MC, simulation is one of the most popular simulation methods which is widely used to calculate adsorption isotherms. Monte Carlo methods are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. What is force field? Force field refers to the basic functional form of potential energy, includes both bonded interactions and non-bonded interactions that describe the long-range electrostatic and van der Waals forces. The FPYEu MOF has been reported by Shai et al. In 2014 with the following molecular formula. FPYEu MOF has two types of linkers, decarboxylic acid and phenanthroline. The unit cell of FPYEu has a total of 16 transition metal atoms. Therefore, it is impossible to achieve the Y:/U ratio of 19:1 in the structural formula of a single unit cell, as only an integer number of atoms can be modeled. Modeling a 19:1 ratio of Y:/U requires at least 5 unit cells with 76 Y and 4 U atoms, but the size of such a simulation box will require computationally intensive simulations, which may not be necessary if the distribution of metal ions in the unit cell does not play an important role in the adsorption isotherm. In accordance with our previous work have been studied methane, ethane, hydrogen sulfide and water adsorptions in FPYEu MOF using molecular simulation and the applicability of the force fields, focusing on the configuration in which the europium atoms are close in a model of FPYEu MOF. It was found that force field applicability needs to be treated carefully, as in all cases large deviation with experimental results are obtained. Notably, these force fields were not developed for a specific MOF. Moreover, the focus was on close configuration in our previous work. In this study, 8 different configurations having europium atoms arbitrarily located in the simulation box were explored to evaluate the sensitivity of distribution of metal ions on adsorption of gases. Noteworthy, the locations of europium atoms have been randomly chosen in configurations. In this work, the focus will be in 1. Using Monte Carlo simulation as a tool to study the effect of the distribution of different metals in the system. That is not possible from experimental methods. 2. Assess the validity of different combinations of force fields. 3. Study the influence of cutoff. Methodology. Models. 8 different configurations having europium atoms in green color arbitrarily located in the simulation box were explored to evaluate the sensitivity of distribution of metal ions on adsorption of gases. Several sets of Lennard-Jones parameters have been derived for methane, which are used to describe the methane interactions in all materials, of which Dreeding, Towhee and Goodbody et al. Are most commonly applied in studies of adsorption. Methane in these force fields is represented by a united atom model with one site. The difference between these force fields is only in epsilon. For Dreeding is 149 Kelvin, and for Towhee or Goodbody et al. Is 148 Kelvin. In this work, Towhee force field was used to represent methane, and the results were compared with our previous work where was used Dreeding model for methane. Towhee force field was also used to model ethane, and the results were also compared with our previous work where we used Dreeding model for ethane. The difference between these force fields for ethane is also only in epsilon. For Dreeding is 125.8 Kelvin, and for Towhee is 98 Kelvin. Kamath et al. Was used to represent hydrogen sulfide. Such a model has been successfully used to reproduce the experimental vapor-liquid phase equilibrium data and has been validated in other previous studies. Simulations were also performed with the OPLSUA force field to compare with our previous work. TIP4PU force field was used to model water molecules. Simulations were also carried out with the SPC/E force field. The calculated isotherms of nonpolar gases in FPYEu MOF compared to isotherms in our previous work are shown in this slide. Although using different combinations of force fields, the calculated isotherms for methane and ethane are still overestimated the experimental ones. Using Towhee or Dreeding model gives very similar results. The results also show that using cutoff radius of 10 angstrom or 13 angstrom overestimated the experimental results. Nevertheless, the differences with experimental data for both gases indicate different non-accessible volumes. The differences with experimental data could be due to the lack of applicability of Lennard-Jones parameters, poor accessibility or accuracy of the experimental isotherms. The results also show that the simulations boxes with different two distributions do not affect the adsorption of different rare earth metals distributions. The computed adsorption isotherms for hydrogen sulfide and water with different force fields and sets of charges are shown in this slide. It can be observed that the selection of the force field for framework can have a dramatic impact on the simulated data. The agreement between experimental and computed data for hydrogen sulfide is excellent over the whole range of pressure by using Dreeding and UF for FPYEu and Kamath for hydrogen sulfide, whereas UF for FPYEu and Kamath for hydrogen sulfide overpredict the experiment data. Nevertheless, using different combinations of force fields for FPYEu has no influence on the simulated data of water. It is possible that modifying the charges of the MOF and/or the force field parameters suggested by Porous, Peritello and Ferenger-Menes may satisfactorily address this shortcoming, although it cannot be modified without verifying the pore volume of the MOF. Interestingly, the calculated adsorption isotherms are not sensitive to the europium atoms distribution in the system. The current work has shown that simulation tools can be used to study the applicability of classical force fields and the sensitivity of the calculated adsorption isotherm to the metals atoms distribution in the system. Different force fields available in the literature were used to model the adsorption of gases in FPYEu, and some of them were applicable, like hydrogen sulfide, where good agreement was found with experimental results, while others were not transferable, like methane, ethane and water, where the calculated isotherms over or underestimated the experimental ones. This may be due to the lack of applicability of Lennard-Jones parameters, poor accessibility, partial charges or accuracy of the experimental isotherms. It is possible that the modifying the charges of the MOF and/or the force field parameters may satisfactorily address this shortcoming, although this was not explored in the present work. Interestingly, the results also show that the simulations boxes with different europium atoms distributions do not affect the adsorption of different rare earth metals distributions. The 8 different configurations having europium atoms arbitrarily located in the system give the same results. This also indicates that modeling different ratio of U:(Y) is not necessary.